Hi friends, today we discuss about the achromatism. First of all, the question, what do you understand by the term achromatism? Explain the conditions when the two lenses are in contact with each other. When the two lenses are separated by a distance. Let's learn about this topic. When the two lenses are placed in such a way that the image formed by them is free from chromatic aberration, the combination of lenses is called as achromatic combination, and the phenomena is known as achromatism. Step by step explanation of the statement. What is chromatic aberration? When a white light passes through a single lens, like a magnifying glass, it splits into colors like a rainbow. This happens because different colors means wavelengths of light bend by different amounts. This effect is called chromatic aberration. It causes blurry or colored edges in the image. The main problem of chromatic aberration reduces the sharpness and clarity of the image. It's especially bad in lenses used in cameras, telescope, and microscopes. The solution is achromatic combination. To fix this, we combine two lenses. A convex lens which bends light inward. A concave lens which bends light outward. These lenses are made of different types of glass with different dispersive powers. The lenses are arranged so that the color spreading means dispersion caused by one lens is cancelled out by the other. As a result, all colors focus at the same point. The result of achromatism, the image formed by this lens pair is free from chromatic aberration. This special combination is called an achromatic combination. The phenomena of removing chromatic aberration using this method is called achromatism. In simple words, achromatism is when two lenses are combined in such a way that they remove the rainbow like color. Blurring means remove chromatic aberration, making the image clear and sharp. Real life examples: telescopes, cameras, and microscopes. Telescopes use achromatic length combination to get sharp images of planets and stars. Without achromatism, stars would appear with colored halos, making observations unclear. High quality camera lenses use achromatic doublets, means a convex and concave lens pair to remove color distortion at the edges of photos. In microscopes, achromatic lenses help in observing tiny biological samples clearly and accurately without color errors. The minimization or removal of chromatic aberration is termed as achromatization. It means chromatic aberration is a problem in lenses where different colors of light do not come to the same focus, causing blurry images with colored edges. Minimization or removal means reducing or getting rid of this problem. Achromatization is the name of the process used to fix this issue. In very simple explanation, when a lens causes colors to blur or separate, we say it has chromatic aberration. When we correct or reduce this color error using special lens combination, that correction process is called achromatization. For example, imagine looking through a camera lens and seeing purple or green outlines around objects. That's chromatic aberration. Using an achromatic lens helps remove those color outlines. That's achromatization in action. Simply, we called achromatism. The convex lens forms the image of violet color closer to the lens than red color. It means a convex lens bends or refracts light rays and brings them to a focus. White light, like sunlight, is made up of different colors: red, orange, yellow, green, blue, indigo, violet, called the visible spectrum. When white light passes through a lens, each color bends differently due to dispersion. Violet light has a shorter wavelength and bends more than red light, which has a longer wavelength and bends less. Therefore, the violet rays come to focus closer to the lens and red rays focus further away. This causes chromatic aberration where different colors focus at different points, creating color fringes in images. The concave lens forms the image of violet color is nearer to lens than red color. It means a concave lens is a diverging lens. It spreads out light rays. When a white light passes through a concave lens, dispersion occurs. Different colors of light bend or refract by different amounts. Violet light has a shorter wavelength and bends more than red light, which bends less. As a result, the divergent rays of violet appear to come from a point closer to the lens compared to red. Violet, more refraction image appears closer. Red, less refraction image appears farther. By the comparison of two cases, it is observed that although the violet color is focused nearer to the lens in both the cases, but the violet color falls to the left of red color in case of convex lens and to the right of red color in concave lens. It means in both cases, violet light focuses closer to the lens than red light. But their positions are different because the lenses bend light in opposite ways. In a convex lens which converges light, violet is on the left of red. In a concave lens which diverges light, violet is on the right of red. In very simple explanation, even though violet light always focuses closer to the lens than red light, its position flips sides depending on whether the lens is convex or concave. It is possible that a combination of a suitable convex lens with a concave lens may be free from chromatic aberration. Such a combination is known as achromatic doublet. It means a convex lens and a concave lens can be combined in such a way that they cancel out chromatic aberration or color distortion. This special lens combination is called an achromatic doublet. In very simple explanation, if we join a convex and concave lens properly, the color blurring problem can be removed. This lens pair is called an achromatic doublet. Next, we will see what happens when the two lenses are in contact with each other. It means that two lenses are placed very closely together, so they touch each other and work as one single lens. If you place a convex lens and concave lens together, they combine to form a single lens system with new properties. An achromatic doublet is formed in such a way that all colors come to focus at one point. It means that an achromatic doublet is made to ensure that all colors of light focus at the same point. So there is no color blurring. In very simple explanation, a lens pair or achromatic doublet is designed to remove color errors by making all colors meet at the same point. That is, all colors have the same focal length. This means that all colors of light like red, blue, violet, etc. are bent and focused equally by the length combination. So they come together at the same point. It's important because lenses bend different colors differently, causing chromatic aberration or color blur. But in an achromatic doublet, all colors are adjusted to have the same focal length. So the image is clear and sharp. In other words, the focal length of chromatic doublet is independent of the refractive index mu. In simple terms, the achromatic doublet is constructed in such a way that its effective focal length is the same for two different wavelengths despite the variation in refractive index with wavelength. For a single lens in air, the lens maker's formula is 1 by f, that equals to mu minus 1 into 1 by r1 minus 1 by r2. This is the equation number 1, where f is the focal length of the lens. Mu is the refractive index of the lens. R1 and R2 are the radius of curvatures of the two lenses. We want to find how the focal length changes when the refractive index mu changes. That is, we want to find the differential of 1 by f with respect to mu. Take the differential of both sides of equation 1. We get differential of 1 by f that equals to differential of mu minus 1 into 1 by r1 minus 1 by r2, where 1 by r1 minus 1 by r2 is treated as a constant with respect to mu. So, apply the derivative. Differential of 1 by f that equals to 1 by r1 minus 1 by r2 into differential of mu minus 1. Since differential of mu minus 1 that equals to differential mu, we get differential of 1 by f that equals to d mu into 1 by r1 minus 1 by r2. This is the equation number 2. This tells us how a small change in the refractive index mu affects the focal length f of the lens. Divide equation 2 by equation 1. We want to calculate differential of 1 by f by 1 by f. Substitute equation 2 in the numerator and equation 1 in the denominator. We get differential of 1 by f by 1 by f that equals to d mu into 1 by r1 minus 1 by r2 by mu minus 1 into 1 by r1 minus 1 by r2. Cancel common terms. Notice that 1 by r1 minus 1 by r2 appears in both the numerator and denominator. So they cancel out. We get differential of 1 by f by 1 by f that equals to d mu by mu minus 1. This gives the relative changes in the inverse of focal length in terms of the relative change in refractive index. The image illustrates an achromatic combination of lenses, which is a system designed to correct chromatic aberration, a common optical defect, where convex lens left side labeled with f1 focal length of convex lens and omega 1 dispersion power of convex lens material. Convex lenses converge light rays and have positive focal length. However, due to dispersion, different colors of light focuses at different points, causing chromatic aberration. Where concave lens right side labeled with f2 focal length of concave lens and omega 2 dispersion power of concave lens material. Concave lenses diverge light rays and have negative focal length. This lens also introduces chromatic dispersion, but in the opposite direction compared to the convex lens. Achromatic combination. When a convex and concave lens are placed in contact and their dispersion effects cancel out, the combination is called an achromatic doublet. This arrangement removes chromatic aberration, making all colors focus at the same point. Achromatic condition: omega 1 by f1 plus omega 2 by f2, that equals to 0, where f1, f2 are focal lengths of the convex and concave lenses respectively. It works. The positive dispersion from the convex lens is neutralized by the negative dispersion from the concave lens. This results in a system that focuses all colors of light at a common focal point. The final result of the achromatic combination behaves as a single lens system without chromatic aberration, improving the quality of the image. To solve this, rewrite the division as multiplication. Dividing by a fraction is equivalent to multiplying by its reciprocal. The reciprocal of 1 by f is f by 1. The expression becomes differential of 1 by f into f by 1, that equals to d mu by mu minus 1. Finally, differential of 1 by f into f equals to d mu by mu minus 1. This can be rearranged, means left hand side multiplication f converts right hand side division f, means 1 by f. We get differential of 1 by f, that equals to d mu by mu minus 1 into 1 by f. This is the equation number 3. Dispersive power omega is defined as omega equals to d mu by mu minus 1. This is the equation number 4. Where mu is the refractive index, d mu is the change in refractive index with respect to color. From equations 3 and 4. Simply, in equation 3, d mu by mu minus 1 replace with omega. We get differential of 1 by f equals to omega into 1 by f. Finally, differential of 1 by f, that equals to omega by f. This is the equation number 5. This equation shows how the change in the reciprocal of focal length relates to dispersive power and focal length. Let f1 and f2 be the focal lengths of the two lenses in contact, and omega 1 and omega 2 their dispersive powers of lenses. 1 by f equals to 1 by f1 plus 1 by f2. This is the equation number 6. When two lenses are placed in contact, their combined focal length can be calculated using this formula. The reciprocal of the combined focal length 1 by f is equal to the sum of the reciprocals of the individual focal lengths 1 by f1 plus 1 by f2. Therefore, 1 by f that equals to 1 by f1 plus 1 by f2. Apply the differentiation rule to equation number 6. Differentiating both sides with respect to their respective rules, assuming f1 and f2 are independent variables or functions of some other variable, take time, and we are performing a total differential. Differential of 1 by f that equals to differential of 1 by f1 plus differential of 1 by f2. This is the equation number 7. Applying equation 5 to each lens gives differential of 1 by f1 that equals to omega 1 by f1. This is the equation number 8, where f1 represents the focal length of first lens. Omega 1 represents the dispersive powers of first lens. Differential of 1 by f2 that equals to omega 2 by f2. This is the equation number 9, where f2 represents the focal length of the second lens. Omega 2 represents the dispersive power of second lens. Substitute equation number 8 and 9 into equation number 7. We get differential of 1 by f that equals to omega 1 by f1 plus omega 2 by f2. This is the equation number 10. For an achromatic combination, f and 1 by f hence should not change with color. In simpler terms, for an achromatic doublet, the combination must be free from chromatic aberration. That is, no change with color. It means differential of 1 by f that equals to 0. This is the equation number 11. Substitute equation 10 into equation number 11. We get omega 1 by f1 plus omega 2 by f2 that equals to 0. This equation represents the condition for achromatism in a lens combination, specifically for a doublet lens where two lenses are in contact. This condition ensures that the combination of lenses will focus light of different colors to approximately the same point, minimizing chromatic aberration. Rearrange the above equation means in left hand side plus omega 2 by f2 converts the right hand side. So minus omega 2 by f2. We get omega 1 by f1 that equals to minus omega 2 by f2. This equation can be rearranged to express the ratio of the focal lengths of the two lenses. So we get by f2 that equals to minus omega 1 by omega 2. This implies that for an achromatic doublet, the focal lengths of the two lenses should be in the direct ratio of their respective dispersive powers omega 1 and omega 2, with an opposite sign indicating that one lens must be converging and the other diverging to achieve achromatism.